time to start. It's 2 p.m. sharp. Okay. So welcome to all of you. Welcome again. And so now we are very glad and further to listen to the lessons of Professor Deng of Chicago. Please, we are listening to you.
Okay. So today I'll talk about this derivation of the wave-Kane equation, starting from the nonlinear Schrodinger equation. So chronologically, this is earlier than the derivation of Boltzmann, but the two proofs has very much similarity and also very significant difference, which I'll talk about today. So of the equation. So if you compare kind of schematically, the thing we do in the case of the Boltzmann. So basically, again, for short time, so it's a direct expansion. And there will be the leading terms, and there will be the subleading terms. Will prove that the leading term converges to the iterates of the wave-Kane equation, and the subleading term, converges to 0. And we have the leading versus the subleading. In a long time, another thing that's in analyze the leading term, we need a lot of kind of analysis. And in subleading terms, we need to do again these construct these combinatorial structures and the combinatorial analysis, basically the algorithm combinatorics. Okay, a long time. In the same way as in the Boltzmann case, we need to do this time layering. I will need to do these ansatz, the cumulant ansatz, cumulant expansion formula if you want. Okay, and then we'll do this analysis of combinatorics in multi-layered so the one difference between the proofs of in this case and the proof of Boltzmann is that there will be much more analytic components than in the Boltzmann case. In Boltzmann case, everything is positive, so you just do the integrals, and the main difficulty comes in the combinatorics. And here we still need to do combinatorics. We'll see there is an algorithm, although the algorithm in this case is much easier than the algorithm in the Boltzmann case. But there is also a lot of analysis, in particular, a lot of oscillator integrals involved, since we are having this Schrodinger equation, which involves a lot of time oscillations. So this first difference. The second difference is that the combinatorics part, the algorithm part, turns out to be already kind of pretty non-trivial in the short time setting. So remember, the short time setting was also kind of open until very recently. And so the short time setting already requires a lot of significant efforts, in the combinatorics, although not as hard as Boltzmann case. Now, on the other hand, extending the short time to long time actually does not require too much extra combinatorial analysis. The main difficulty in extending from short time to long time, of course, apart from these equivalent formulas, the main technical point is actually in the analysis. There is a very subtle cancellation, which due to this time is strongly related to this time oscillation that will be needed when you do the long time results, which is related to this error of time. But on the other hand, the combinatorics is essentially the same in the long time and the short. So this is in kind of sharp contrast with the boson setting. In the boson problem, where the short time there is almost no combinatorics needed, but long time there is a huge amount of combinatorics that is needed in this case. Okay, other than that, on the schematic level, the true proof is still pretty much similar, following this framework. Okay, so let me start with the setup of the problem, and we'll gradually get into the analytical part and the combinatorial part. We start with the cubic Schrödinger. Of course, I emphasize that this whole theory can be developed for any dispersive equation. The Schrödinger is a kind of simplest model. Okay, so U is on the torus. U is a function of torus. So torus of size L. Okay, and we have this random initial data, which is given by this. Okay, so this is just normalizing factors such as this the L infinity norm of this guy is equal to 1, and then this is ZL is just so ZL is L minus 1 times Z, and this phi k is a non-negative Strauss function, which will be the initial data for the wave function equation, and GKI the Gaussian random variables, and this is the Fourier coefficients. Okay, so this is the setup, and of course there is a parameter L, which is called infinity. Remember the degree of freedom in this system is L to the D, and there is a parameter alpha, which goes to 0. So L infinity and alpha, we assume there is this scaling law, which is L to the minus gamma 0. Well, why gamma has to be between 0 and 1, I'll not explain. It has to do with something, something that occurs in number theory kind of argument here. But okay, so gamma is something between 0 and 1. And then there is this kinetic time scale, T kinetic, which is equal to alpha to minus 2, which you can write as L to the 2 gamma. So again, as I explained, so this is the first time where this the nonlinear, the nonlinearity is starting to have effect on the statistics of the solution. The thing you have a if you have a nonlinearity being size alpha, then usually you're going to see the effect of nonlinearity at time alpha minus 1. But since you have random data, there is a cancellation happening when you iterate these nonlinearity. So we really see is time alpha minus 2. So this is the candidate. Okay, and the question is, is the limit behavior as L goes to infinity of this second moment, let's say. Of course, there are higher moments, and if you think of Brownian chaos, then let's just think of the second moment. So you already rescale the time by this kinetic time. So here T is O of 1, and then K is arbitrary frequency. And look at this. Okay, so the first thing we do is we, as we usually do with these dispersive equations, we switch to the study of the profile by taking back the linear flow. And moreover, since there is a QE term here, there is this weak ordering renormalization, if you want, that is needed to remove the self-resonant fractions in this U square U. So basically, subtract the mass of U. So by doing this, we can define this profile. in which you take by linear flow, you do the renormalization, and you can also do the rescaling time by this t kinetic. Define this AK of t is equal to, I'm omitting some various pi's and 2 pi's here. Okay, so this is taking back the linear flow. Then we have this renormalization term, you subtract the mass, and then you have and then this is a time rescaling. So if you define this AK, then there is a simple way to write down the evolution equation for AK. So there is no linear term in the evolution equation for AK, and then we have this right here. So dt AK is equal to C plus A bar A at K. So this cubic term C plus, let me write it here. So C plus minus just a conjugate. Okay, there is a factor L to the gamma. Gamma is this gamma here. We have a plus minus I. Okay. This is just the equation for the convolution equation, the equation for wave numbers, and this is saying that you have no resonance, no pairings within this cubic term. And you have e to the I omega t. Okay, so this is a cubic trilinear term that's defined this way. Here, the omega, of course, is a thing that keeps information of the dispersion relation. Omega is basically the resonance. Okay, so this is a thing. We start with a cubic Schrodinger equation. We since this is Laplacian, and then we start with this random initial data, and we define this profile, which reduces us to this direct time evolution. And then, of course, we can do the iterate. We can start doing the iterations by just integrating this formula, right? AK equals AK0 plus integral of this. And the right hand side, you can keep writing, expanding as it in terms of integrals, and get this example. Okay, so now this is the setup, and now let's start with a short time theory. So as opposed to the compared to the Boltzmann case, here we'll spend more time, actually much more time, on the short time theory, because a major part of the notions, of the combinatorial structures, molecules, and algorithm actually already occurs in the short time case. And we'll see in the long time case there is one kind of two or a few kind of key ingredients that is needed in the long.
And so you're already restating the time here, no? So there
Yeah, there is a key kinetic, yes.
also in the formula for it.
Yes. I omega.
Okay. And also in AK at music online.
In where?
Well, the
Yeah.
normalization. Yes.
Yeah. Okay. So we'll start with a short time. Short time means that since we're already rescaling, so T is what should I say? And in this case, we'll just do a direct expansion starting with this formula. Which is we expand iterating this yellow box off. Okay, so what we get is that so it's AK of T sum over all the T, which are ternary trees, JT KLT. So of course, let me explain that this sum is not an infinite sum, it's a finite sum, so there is a truncation. But exactly how much and what level you truncate is important, we'll explain that later. For now, let's just think it's a formal sum over all the ternary trees, and JT is the expression depending on the ternary tree T. Okay, ternary trees obviously is because you have the time unit gets your cubic term. So if you have a linear evolution is 1 point, and then you have a first iterate, you have this cubic, and then each of them can be further iterated, so get a term. T is a ternary tree. And since we have here A and A conjugate, naturally we're having the signs of different nodes of the tree. So we're assigning it such that so T, example T is like this. Okay, that's it. There is a plus. If you have a plus sign, then the 3 children are always kind of a plus, minus, plus. And your plus sign, the 3 children are plus, minus, plus, and then plus, minus, plus. So this is a sign. The sign corresponds to the whether you have a conjugate or not in your input. And then each node we have a corresponding wave number. So these are called decorations. So this wave number is K, and this is K1, K2, K3, and this will be K4, K5, K6, K7, K8, 9. These are decorations. And then we have these, the convolution equation, for example, K equals K1 minus K2, K3, for example, K1 equals K4 minus K5, K6. Okay, so this is the ternary tree, and what is JT? Let me write down with JT.
The minus has not chosen.
So which minus?
K2.
K2 is not expanded, it's a leaf in this case. K is a linear input, initial data in this case.
But generically, a minus leaf can have.
Yeah, it can have. Yeah, I'm just drawing. Okay, this is there is a factor to the minus n gamma times the product. Let's call it n. Okay, so M is the number of branchings in this ternary tree. So this guy has 1, 2, 3, 3 branchings. So M is number of branchings. And here this N is taking the product is taking over all the branching nodes. So this is the branching node, this and this. And the theta N is a sign of N, either plus or minus. Okay, so this is a symbol, like like either plus one, plus minus one, or plus minus I. Matter. This is the negative power here. And here I got something all the decorations, all the wave numbers. Okay, and so here L is a leaf. Let me say L is a leaf. Because leaves correspond to these final inputs, which are our initial data, which is these independent Gaussians. And you have these inputs or the profile, the intensity or whatever, this square root of 5 times the independent Gaussians. And again, see the L is a plus or minus, indicating whether I have G or G conjugate. And then you have this, which has with the time integral. Remember here, if you take dt, you have this. If you recover your integrate, you have this integral in t, and integral in t, you're integrating this oscillator factor in t. So you have this kind of omega and t kinetic, omega n, t n, and theta n is plus minus 1. So it's just this oscillator integral in all the time values. Okay. So this integral is a very important thing. So let me just say that think of this, if you integrate Tn, you're getting a denominator of 1 over omega n. So this is something like product in n 1 over omega. Something like this, which means it's almost summable. 1 over omega is almost summable in omega. We think it's summable. So this is summable in omega n, and later on we use this fact so that when we estimate this, and later on we estimate these couple expressions, we're going to be able to fix the values of omega n using the summability or almost summability of these inputs. Okay. In any case, it's this thing. We have the negative power, the sign, and this is this is initial input, Gaussians, and then we have this time integral basically behaves like this. Okay, so this is the AK. Okay, and then since we're interested in the second moment, which is just second moment of AK, and let's just think if you take the second moment, you have the expected value of AKT and AKT bar. AKT is this sum, and AKT bar is another sum over another ternary tree, and with conjugate. And if you put these together, you're going to get correlation of JT1, JT2 bar. Now, if you formally think of it, JT1 is these are just deterministic. There are no random. No random is coming from these Gaussians. Now, you have a JT1, JT2 bar. You have a bunch of Gaussians. Multiply, correlate with another bunch of Gaussians. You just get these multilinear correlation of Gaussian random vectors. And for that, we have this so-called weak formula, which is very simple formula that tells you these correlations of Gaussians can be written in terms of the parents. Let's see if we have the then we take the expected value of a product J, G, Kj, see the J, plus minus. So this is the sum over all the pairings P. The pairing is any division of this index set J into 2 element subsets, and then we have a product in A. So for any 2 element subset A, let's call it Ij. So Ij, and then we have an indicator function of Ki equal to Kj. and you can indicate a function of sine theta I equals negative theta j. Okay, so basically you are summing over all the pairing such that you have a 1 plus and 1 minus being paired in the exponent. And then in this pairing, you must have that these two things are equal because the correlations of independent Gaussians are 0 and correlation of same Gaussians will be 1. Okay, so in any case, here you see if you these Gaussians occur at the leaves of the trees, and if you have by this formula, going to sum over all the pairings of all the leaves of the trees. So then we define a couple. Couple Q. This is tree P plus. So here P plus means its root has sign plus. You can have your root can have sign plus or minus, and determine subsequently the leaves. Tree T plus with root plus a tree T minus with root minus, and the pairing T between plus roots, plus leaves, and the minus leaves in T plus union T minus. So let me emphasize that you can have pairings between two leaves in the same tree. You can also have pairings between two leaves in different trees. And all of these counts as a part of a couple. Okay, because this sum here, it doesn't distinguish whether these I and J are in the same tree or different trees, and you can allow for all kinds of pairings. So then we get this formula, which only depends. Okay, again, here this sum is for now it's arbitrary, but we'll actually truncate it and we'll have an error term and we'll need to deal with error term. Okay, so Q is a couple. And the KQ is the following. Of a sum L to the minus M d minus gamma. Here M again is the total number of branchings in the couple Q, which means in both trees. Then we have a sign. Okay, times the sum. Again, also the declarations. Except that now you don't have Gaussians. The Gaussians are kind of cancels each other, and you have the square root. But you have two square root, you just get 1/5. So let's say you have a product L leaves. Let's call it plus leaves, because the leaf pair contains 1 plus or minus. So let's say phi L. Okay, and then you have the same thing, this integral e to the I kinetic omega theta n. Yes. Okay, now here except that this integral now is in the time variables in both trees. Okay, so let me draw an example. So example here, let's say you have a couple. Well, couple means you have two trees. Let's say you have since you want the branching and the negative leaves. So you can have arbitrary pairings. Again, here let's use different colors to indicate different, pairings. So have this red, this red. Then you're going to have a green. Going to be this minus. And you're going to have example. So this is a couple. You have two trees, and you have each, this has this, this has this, this has this, this has this. And so if you have the, K, K1, K2, K3, then this will have to be K3. You have a K4, 5, and this also K, and then this will have a K1. Plus one thing, so it's rather so this is D. So D decorations. Okay. KL1 equals KL2 if leaves L1 L2. Okay, this is K3 and this will be the K4 and this will be K4. So this example of pairing and declaration of pairing, and obviously by applying this formula for JT and applying this Weeks formula, you get this formula for K. Okay, so these are just formulas. This is, for short-line formula, this is pretty easy to write down. And the question is now we need to analyze, what are the asymptotics of this cake. Okay, any questions at this time? Okay, yes.
We get this formula, the AK squared, where when you square AK, you suddenly the pairings between roots with trees with roots in positive roots.
Yes.
Negative roots. Also understand why.
So, I mean, you have a AK times AK bar.
Yeah.
AK is a sum over these positive trees. AK bar, the conjugate, is will be a sum over all negative trees. And you couple these two, and each trees you have this formula with a bunch of Gaussians. On negative tree, you have the same formula with a bunch of Gaussians. And then you use Weeks formula to pair these Gaussians, which corresponds to the leaves. The leaf pairs in this couple.
So AK is only a sum of positive trees.
Yes.
Okay.
Okay. Okay. So this is a formula, and now next thing is how do we analyze and pick. So before we talk about the general case, let's look at the simplest case, like the lowest order case, because we're going to see, for now I haven't explained like how do we get this Waking equation. So we'll see how to get this Waking equation by looking at these lower order kind of diagrams, in these couples. For examples. So if we have let's say if we have two trees, both being trivial, that means you have a leaf with another leaf. This obviously will get you the initial data, because that's the square root of 5, and you only have one square root of 5, you just get square root of 5, which is the initial data. Okay, so following the next order thing would be where you have 1 plus 3. Let's say you have 1. This. Okay, so this thing will be the next term following, but this thing will be 0. This thing vanishes because if you have this K, K1, K2, K3, then the parent condition would force K2 equals K3, but then this is forbidden since we are we're dealing with this this term. We already removed this mass. So this term is equal to 0. So the real next term is when you have this. You have okay, so this is a cubic, and also there is a term which is a linear quintic. We have let's say this. Okay, so this is a cubic, this is linear quintic, and this term turns out they are going to converge to the second iteration of wave equation. Okay, and in fact, so this structure, like how if you keep iterating the structure, for example, you have this 3 kind of cubic thing, but then if you have a cubic, then at each leaf pair, each pair of leaf, you can also expand it by replacing this leaf pair with another cubic. So you have here, you have a cubic of this pair with this pair with this pair with this. Okay, in the same way here, for this green leaf pair, you can also expand it and say this pairs with this pairs with this pairs with this. In the same way, for each of the leaf pairs, you can also replace it by a linear quintic by the same way, and you keep iterating this. This turns out to produce an important class of couples, which we call the regular. We call it, by iterating this, we get these regular couples. And the point about regular couples is that they exactly correspond to the high order iterations of wave equation. Higher order iterates. And of course, you can also do it by iterating the way. Okay, and this way you'll see that precisely those regular couples that are going to contribute to wave equation. Again, everything is in the short time setting, and those non-regular couples that are going to vanish in the limit. So let's look at the regular, or let's look at this couple. So let's just do the calculation for this cubic. You can do the quintic, linear, and similarly. But I'll show you, how exactly you get the solution of wave equation. If you plug in the formula like KQ. So by the way, in our paper, these things are called mini couples. These are called basically the mini couples. They are smallest kind of smallest examples of regular couples. So let's see, mini. KQ. So we have a sum. Now you see here you have a K, K1, K2, K3, and here this K and is the same K1, K2, K3. So only have a sum over 3 variables. 1 minus K2 plus K3 is K. Okay, and there is a non-resident condition, but you don't need it because this will lead to low order terms. And then you have this okay, so I have a phi K1, phi K2, K3 times there's this time integral. With time integral, the time integral 0 to t, integral 0 to t. So e to the I so c the n 1 plus is 1 minus. So I have t kinetic omega t1 minus t2 dt1 dt2. Because this is one thing comes with positive phase, one thing comes with negative phase, t minus t2. Okay, and this thing you can write it as So there is a negative power here, L to the L minus 2D minus gamma. Okay, and then you have phi K1, phi K2, phi K3. You can calculate this integral, which is pretty easy. You get T kinetic times omega, and then you have this e to the 1 minus e to the I T kinetic omega times T square. Basically something like this. And then you notice that if you sum your K1, K2, K3, now Kj belongs to this mesh of size 1 over L. Okay, so this sum is approximated by the Riemann integral. So formally, and you can justify it like using a bit of number theory, that then it's going to be, so L to the minus 2D times this gets you like L to the minus 2D times the sum gets you the integral. Remember, Kj is each Kj, the sum is L to D times integral to L to 2D. So you have this L to the gamma times integral by K1 minus 21, so delta function by K2. 3 delta of K1 minus K2 plus K minus K, and times this thing. This thing can write it as minus 1 times times omega square, and have 1 minus e to the I T kinetic omega T square. Okay, so so this is dk1, dk3. And then so here this omega square, so which is a function of omega that is in L1, that is integrable. And then you can rewrite this guy as a rescaled, L1 function, which you can think of it as a approximate identity. And then in the limits, where the T kinetic goes infinity, so alpha goes 0, T kinetic goes infinity.
Excuse me,
Yes.
so what does number theory mean here?
Number theory means that because you see this thing here is basically you're looking at this omega being less than a negative power of T kinetic, which means that you're considering you're counting those lattice points in mesh over L that is close to a certain hypersurface. Okay, and this in a certain regime of scaling laws, it requires a number theory. Okay. But here is formal. Everything is formal here, which can be just as I said with number theory. So in the limit T can equals infinity, we're going to see that this thing that's you can check. I'm not going to write details here. So this is going to approximately be T times delta of omega. Okay, and again, if you think alpha to gamma, T can minus 1, this thing cancels each other. And then so the whole thing converges to this integral phi A1 T times 1 K2 K3 delta of K minus K, so 1 minus K2 plus 2 minus K delta of omega K1 dk2 dk3. Okay, so you can check yourself, but this is a formula. You see, it is precisely one terms in the right side of the equation. The term with phi k1, phi k2, phi k3. It corresponds to this picture. Of course, if you have one of these pictures, there are three cases, and these three other cases precisely correspond to the three other terms. We have 5K, 5K1, 5K2, 5K3, 5K1, 5K, 5K3, and 5K1, 5K2, 5K in the wave equation. Okay, so there is a lot of analysis and as I say, a bit of number theory involved here, but in the end, you can see that these mini couples, they exactly lead to the second iteration of wave equation, and the higher order, the iterates of these mini couples or regular couples exactly correspond to high order iterations of the wave. By the way, everything here is homogeneous. In inhomogeneous, you have to consider X, which is more complicated, but I'm not going to talk about it. Okay, so this tells us about this regular. Okay, so regular couple case.
Can you explain where is the second iteration of the wave kinetic equation? Because I'm not sure I can see the difference with the previous formula, the one that you erased.
Sorry.
So this is actually the first iteration?
No, this is the second. This is the okay. So the first iteration is a linear thing. It's initial data. Okay. If you expand the wave equation, and the first thing being initial data, the second thing being this cubic integral, which is this.
Okay.
Oh.
Okay.
So this takes care of all the regular couples. And now let's go to the non-regular couples. Like the non-regular couples, they should vanish in the limit. Of course, it's a problem. How do you prove it? I think we can start with so here we have a kind of very nice, very useful lemma which describes the structure of general couples, okay, arbitrary couples. So there is this lemma here. For any couple, regular or non-regular, there exists a unique couple, which you call Q tilde, which does not contain any regular structure. I'll explain what is regular structure. Such that Q is formed from Q tilde by attaching, regular structures to each leaf pair, each branching node, of okay, so here let me explain what is a regular structure. It's just a regular couple, but there is another case which we are calling a regular tree. So that's a mini structure at the first. This equals a mini couple. Okay, and of course there are others, all. So. Or this, or there is something called mini tree. Basically, is something like this. You only have two leaf pairs, and this doesn't need to be a leaf. This can be anything. Okay, so this could be a leaf, but then you pair with another leaf, and you get this mini couple. But then this could be anything. This could have a further kind of branching. This could have further branching above and below. Okay, so only thing is that you're looking at this particular part, which we call mini tree. Okay, so in general, you can consider for any couple, you can attach a mini couple here. For example, if you have any couple, so whenever you have a Q there, and then let's say you have a leaf pair downstairs, then you can always replace this leaf pair by a mini couple. Like you can, no matter what happens in other phases of the couple, you can always do this. Okay, in the same way, for each branching node of any couple, okay, so there is a branching node here. You can always turn this into okay. So you can always turn this thing into a mini tree, and then so whatever happens there is whatever happens there. You just replace this single point. Replace a single point by this mini tree. Okay, so since it is not quite a couple, it's effectively there is nothing different between this and a couple. It's just some structure that can insert into a couple. And then here's a lemma. So any Q that exists unique one that does not contain any regular structure, such that Q is formed from this Q by attaching regular structure. So each leaf pair and each branching node. So for example, if you start with this Q tilde, okay, start with this tilde, let me draw it this way. So okay, it's a red. I'm drawing kind of pretty arbitrarily, like let's say green, yellow. So okay, so you can think in the Q tilde, this is a node, this is a node, and these are leaves, and they are paired like this. But in Q, really, what happens is that this is a regular tree. So regular tree means you are iterating this mini structure. You can iterate, you can start with a mini tree, you iterate, put another mini couple, put another mini tree, and the way everything you get is called a regular couple, a regular tree. So here this is not a node, but this is an arbitrary regular tree, and this arbitrary regular tree, and this arbitrary regular tree, and then this red is an arbitrary regular couple. And this is arbitrary regular couple, and this guy is arbitrary regular couple. And so on. Okay, so you see that really this Q tilde is a skeleton of Q in the sense that you're attaching a bunch of regular because you know how to use regular structure. The regular structure is exactly giving you these iterations of the wave equation. You know how to calculate. So they are this thing that you know. Okay, so then the only thing is that you have this skeleton, and what really matters is the size of the skeleton instead of the sizes of the regular couples that you are attaching. This is the point. So we plot Q tilde. So now let us answer the question we had earlier. What is the order of expansion like in this whole trees and couple expansion? Okay, so let's see. Suppose we expand in expand to order A. Okay, so you have order A. Then it is known that the number of couples, because we are summing over all the couples, with their component factor, is about A factorial, or maybe 2A factorial. Okay. So then, if you look at the worst case scenario, those coming from regular couples, the size of KQ is less than T to the A. So basically, you see that this corresponds to either rate of the wave equation, which you grows decays exponentially in A for T to small time. But if you use this upper bound and use this upper bound of couples, you will see divergence because T to A times A factorial is going to diverge if A goes to infinity. So we need to refine this analysis. We need to classify the couples. Like we will show that for some couples we are having this sharp bound, and so for some other couples we are actually gaining more powers. And this is precisely using this lemma. We define this index rho to be the size of the skeleton. Define index rho of Q equal to the size of Q, the number of branching nodes of Q. Okay, then we have these following two things. The number of Q with rho Q equals rho is bounded by rho factorial times C to the A, where A is the size of Q. And this is because once you fix the size of rho, you fix the size of Q tilde, and if you draw this couple Q tilde, which now have only size rho, you're only having this rho factorial choices. But then once you fix the rho factorial, once you fix the skeleton, then you attach these regular objects. So there's an easy lemma that tells you the number of regular object grows only exponentially with a absolute constant to the size. And then so if we attach back these regular structures, you only have exponentially many choices instead of factorially many choices. And now this will get this exponential growth, which is fine because we have this exponential decay. And then next is for each Q with rho Q equals rho, we have this KQ of PK uniformly less than T to the A times L to the minus beta rho, again for some possibility. And again, this allows you to close this as long as rho is rho less than A less than log L to the constant in the same way as in the Boltzmann case. So you see that this rho it essentially plays a role of recreation numbers in the Boltzmann case, although I mean it's kind of post theory, like we don't have a good a very physical intuition explanation, why do we need this particular rho? How do we interpret this in the form of recreations? But this is some definition of index that works. And this rho is not really unique. It's you can play with it a little bit and between various equivalent things. But this will allow you. Okay, maybe we spend a few minutes describing the proof of this, how exactly to prove this. This needs a notion of molecules. Okay, so basically we are starting with the trees. We are building up, building up the couples, starting from trees, and then we're turning these couples to a notion of molecules. And the notion of molecules is designed such that you are seeing this these equalities, these equations in this definition of KQ directly without any other structure that is not useful. Okay, so let me explain what is a molecule. But really, but before talking about molecules, let me say something about that Q is the sum of all decorations of this of this integral of something, and we said that integral is e to the I t kinetic t and omega n minus. Okay, and we know that this is basically bounded by product in n T kinetic, I forgot to write T kinetic factor here, T kinetic omega n here. Okay, and you know, this guy is summable, almost summable. So this KQ is effectively bounded by sum in D declarations, the indicator function of less than 1, or maybe it belongs to a unit interval. Okay, so this is effectively a counting problem. You see, you are counting all the declarations, all the choices of the vector variables. Remember, for each leaf or each node, you're having a variable, and you have this this momentum equation at each branching. So k equals k1 minus k2 plus k3. And in addition, you're having this relation, which tells you the omega n belongs to the interval of this T kinetic minus 1. Okay, omega is k square minus k1 square minus k2 square plus k3 square. Okay. And then this also we're having this equality at each branching node, and this quadratic, basically let's say equality. I mean it's inequality, but quadratic equality in this. Okay, and these were counting the number of declarations, which is the main technical ingredient in this estimate of the cake. Of course, there are lots more, the number theory thing, the Austrian inverse thing, but never mind. The main technical thing is counting the number of choices for each of these vectors. And because we only care about this counting, now we no longer need the other structures, who is the parent of who, who is the left child, middle child, right child, we don't care about them anymore. So we can turn this a couple picture into a molecule picture where we only show the properties of these variables and these equations. So this idea. And then what is a molecule? A molecule is this. So the atoms are the branching nodes in Q. Here Q is couple. We're going to turn this couple into molecule. And then the bonds, which are the variables involved in this declaration. For example, if you have a let's draw a couple here. This is a plus, this is minus. Say, this is okay. Let's say you have a K, K, K1, K2, K3, K4, K3, 5, and this is K4, K2, K5. Okay, so let's say, so the branching nodes are this, and this. Let me draw this. So these are 3 atoms. Okay, these are 3 atoms of the molecule. So we can call it number A, number B, number C. A, B, C. Okay, and what do we mean by the bonds are variables? So see, if you look at this branching node A is associated with 2 equations. The equation involves K, K1, K2, K3. Okay, we have a momentum equation, we have a resonance equation there involving K, K1, K2, K3. On the other hand, at this atom C, there's another set of equations involving K1, K4, K3, K5. Okay, so this is a root, this is a root, so this parent is 3 children. There's an equation involving K1, K4, K3, K5. Now these 2 set of equations, they have 2 common variables. K1 is a variable in common. It occurs in both this equation and that equation. K1 occurs, and K3 occurs in both equations. You have K, K1, K2, K3 in one set of equations, and have K1, K4, K3, K5, another set of equations, and this K3 is involved in both set of equations, again, by this pair. Because of this, we are putting two edges between this atom A and atom C, because to indicate that we have two common, variables involving the two sets of equations. Now, what about A and B? You see A and B, there is, K, K1, K2, K3, the K, K4, K2, K5. Now, K is fixed, we don't count. So we think K is fixed, we don't count. There is no summation in K. So we have only one pair of common variable, K2. So there we put a one edge, from between A and B. So there's one common variable, K2, that is sum over. Same thing with B and C. You see B and C here. On B here, you have a K, K4, K2, K5. On C, you have a K, K1, K4, K3, K5. The K4 and K5 are the common variables. So you put two edges, between B and C. So basically, you see that the common variable here is K1, K3, is K2, is K4, is K5. So this is the model.
Can you explain again why you didn't count K?
K is a fixed variable. K is not sum.
Okay. It's not sum.
Yeah. Okay. So this is this molecule, and the thing is that at each bond, we have a variable. At each atom, we have a set of equations. Okay, and then we are looking at the counter problem. This number of solutions to this system, which is number of solutions to this system for this molecule. And okay, you just have K2, K4, K5 have satisfying equation. Of course, with K, but K is viewed as fixed. So the equation for K2, K4, K5. There's equation for K1, K2, K3 again. There's equation for K1, K3, K4, K5, which is this. And then once we reduce to this molecule, we can start doing the operations or cutting operations of the molecule, which is follows the same idea as we did for Boltzmann. I mean, there are two differences though. But one difference is that remember in Boltzmann case, there are not only bonds between connecting two atoms, so there are also these free ends that goes from one atom without another atom. So there are these ends. So this is bond, this is end. Now in this case, we don't have ends. Everything is a bond. Okay, so every edge is a bond that connects two atoms. And second is that in the cutting sequence, like when we cut a degree, cut a certain atom of degree, like in the wave candy case, we have degree 4, which is bad, which is the same as the Boltzmann, and degree 3 is normal, which is the same, and degree 2 usually doesn't gain anything, which is also the same as the Boltzmann, except that there are also cases where degree 2 can be bad, but then this leads to a little bit of discussion with cancellations. But then the difference here is that degree 1 is also acceptable. And if you recall, like in the Boltzmann case, we can never allow any kind of degree 1 thing. You have a severe singularity there. But here is different. Since we are looking at the summation, counting problem instead of the integral. So there is no delta function here. So actually, you can allow for these kind of degree 1s. You don't need to worry about them. And this is, in the end, this is the reason why the algorithm in the wave turbulence case is much simpler than the algorithm, corresponding algorithm in the Boltzmann case, because there is no singularity. You don't have these direct function you see in the integral. I think ultimately it is due to the fact that in the Boltzmann problem, you're considering a kind of low density limit, and while in the wave candy problem, you're considering kind of weak coupling limits. Okay, so this is the thing, and I want to say the good is the same, the 3 3s. The degree 3, and degree 3s are precisely the good scenarios you are hunting for. Okay, and let's see this one. This one is easy because already A is degree 3, B is degree 3. You have degree 3, and then degree 3, and you are good. You just remove it. and you look at C, okay, C is trivial. When once you fix it, there is nothing with C, that's the instrument. Okay, so in general, the algorithm, so once we, we reduce from the, this integral thing using the almost summability, reduce it to the counting problem, and using from the counting problem for couples, reduce to counting problem for molecules. And for molecules, again, we have just as the Boltzmann case, we have a counting estimate for these three subsets, three molecules, we're counting for 4 molecules, for this is trivial, of course. And then using these, elementary, we didn't call it elementary yet in the way only spectrum, but we call it using these elementary, counting estimates. Again, we reduce to the question of whether we can perform a cutting sequence of a molecule such that we produce enough many good things. And of course, there will be no bad thing, there will be only one bad thing, which is fine. That we produce sufficiently many good things. And in this case, an algorithm, it's actually pretty simple. Just to say that we list a set of good structures. So these three is a basic example of good structure, but there are more good structures, like let's say the 3-3 good structure. And if you have a double bond between a 3 and a 4, this is not a good structure. Or if you have a double bond between a 3 and 3, this turns out also to be good structure under some assumptions, and so on. So there's a finite set. I mean, I'm not but it's a finite set of good structures. Okay, and then it's very simple, just greedy algorithms of if there exists, good structure, cut it. Otherwise, cut anything, any single atom. It turns out that the algorithm in the wave kinetic case is much easier than the Boltzmann case, that you just do this, and you can, by counting a few kind of invariant quantities, monotonic quantities, you can by elementary ways you can get to this this lower bound. You get this lower bound number of good components is almost guaranteed. Of course, as long as you are kind of the skeleton that don't contain any regular object, and your size is large. Yeah. Okay.
So this discussion is just for the skeleton, or is starting from the structure?
This is just about skeleton, because you already remove the regular. You know how to do the regulars. You just only look at skeleton. Okay, so I have maybe 20 minutes. I will talk about 2 more things. One is the cancellation, and another is a long time. So unfortunately, I don't have much time for long time, but so the cancellation comes with a specific set of structures that is not the regular ones, beyond the regular ones. So it turns out there exists there also exists special structures which in the molecule picture corresponds to this, to these double bonds. I really double bond chains. You can have long chains of double bond. Or there is this special structure of these triangles. I mean, the triangle is a subset. There's a class of 8 such triangle is one of them. So there are these triangles that if you look at these corresponding KQs individually, you are going to get a bad estimate in the counting problem. It's bad. However, what we did is that we started from these bad structures. We proved, in the molecule theory, that these are the only bad structures. So there is if you look at our paper, there are kind of a set of 8 kind of structures of this form, 8 families of structure of this form, and these are bad. But then what we did is that we go back to the couple picture. Notice that a couple corresponds to a molecule, but the molecule can be recovered from multiple different couples. And then precisely we see that for each of the molecules in this set, we found, you know, the couples forming this molecule, they are kind of turned into pairs, and each pair has extremely subtle cancellation. So I'll show you one example of, I'll just show you one. So this corresponding to this, okay? So there is one here, one here, one here, one here, two here, two here, two here, two here. And there is number 3 here, number 3, 3. Okay, turns out that this, of course, the other things that are unpaired, they are just arbitrary things. They can branch, they can do whatever they want, and the rest of carbon molecules are the same. The only difference comes from the positions of these 3 leaf as red is the same. This blue and this, so this green and this blue and this green here and blue. You see these 2 pictures. If you just look at on the level of couples, they are very different. They are not even like homomorphic. So it's hard to see like why they will be canceling between this term and this term. And it turns out that if you draw this in the molecule picture, you get exactly this, and they get the same molecule, except that there is the correspondence relation in the going from the couples molecule in one place is different. Okay, so it turns out, and we still don't completely understand the mechanism, that there is a cancellation between this and this, which has to do with some kind of when integrate, you have a okay, so we have a sum, k1 minus k2 plus k3 equal to k, and we have e to the it omega and something. So if you look at this sum, kind of the leading term in this summation is going to have a delta of t. It's the point at t equals 0. And then if you look at these 2 terms, if you put the combination into them, so you're going to have exactly something like integral, t1 less than t2 less than t3, or something like a sum k1 minus k2 plus k3 e to the I t1 minus t3 omega and some other factors. And if you plug in this formula, you get exactly delta of t1 minus t3, and precisely because you have these time orderings, t1 less than t3 between t1 and t2, if you have a delta of t1 minus t3, and this integral would vanish because t2 had nowhere to go. So, and on the other hand, if you have these individual things here, then T2 wouldn't be just between T1 and T3. The left term will correspond to the integral with T2 bigger than T1 only, and the right term will correspond to the contribution with T2 less than T3 only. And then if you combine them, you get T2 bigger than T1 less than T3, and precisely here you get a cancellation and not in any of the individual terms. So this is something we still don't fully understand, but it's something very interesting that's presumably something we can be look at further. Okay, so this is cancellation structure, and everything here is in the short time setting. Okay, so let me, in the last maybe 10 to 15 minutes, let me very quickly kind of explain what is the main points in the long time setting. You see the short time setting is already kind of as complicated as this, but fortunately, this long time is mostly kind of conceptual new ingredients. So it's technically there are still a lot, but But we don't need, for example, we don't need any new algorithm. The algorithm is still the same. This is in sharp contrast with Boltzmann, where you have this whole lot of things in the long tree. But so the starting point is the same. So we have the time layering. I'll use L, Q, okay, we'll do this time layering. And then again, we're going to find some answer. You know, in the time 0, we have independence, and the time later on, we don't have independence, we need the answers. Okay, so time 0, independence. And if you have time Q tau, what we have is that we're looking at these mixed moments or kind of correlation between different frequency, different modes. We have this expanded value of let's say A1 of Q tau, theta 1, AK2 theta 2 Q tau, AK2S Q tau to the theta 2S. You only have an even correlation, otherwise it's always 0. Okay, so this is going to be a sum of cumulants. Now here we need is there any?
Yes, no, it's the camera that
Okay.
is living its own life.
Okay. Okay. So the cumulant here is actually more precise than cumulant used in Boltzmann. We need to kind of factorize out everything and not just factorize out the single variable function. To factorize out all the everything you can possibly factorize. So here you have a sum over partitions P, partitions of 1 to S. Then we have a product A being a set in P, a set in partition, and then we have this K, which is a cumulant of A eta A Kj theta J Q tau J in X. And then we're going to have these ansatz, a formula for these cumulants. And what are these cumulants? K of A Kj theta J Q tau J belongs to A. So this is going to be a sum. Okay, if you have a 2-point correlation, it's sum over couples. If you have a two S point correlation, it's going to be a sum over a structure formed by 2 S trees instead of 2 trees. I'm calling it a garden. Garden of these many trees. Okay, and you have this Kg of this A1, Kj, J belongs to A. Okay, and this is a similar thing defined similar to the couples, but we sum over all the variables and integrating all the variables associated with these gardens. And then this garden will have to have a satisfy a specific property. So G is what is so-called canonical garden. Then this property basically corresponds to the fact that the property in the Boltzmann case that any particle lines any particle is connected to another particle downstairs in this whole set of layers. And this canonicity is an analog of this property somehow in the wave set. And then we need to analyze this Kg. Of course, we need to prove this by induction. Of course, you just iterate. Like if you have this formula for the previous layer, then in this time layer from Q minus 1 to Q tau, you do your Duhamel, which corresponds to the class expansion in the Boltzmann. You do Duhamel, and you expand this thing at Q tau in terms of the correlations at Q minus 1 tau, and do the same thing. Okay, and then you can prove this formula by induction. And once you prove this formula by induction, you just need to estimate sketching. You know, estimate H. And to estimate this KG, again, you look at these, these regular couples and skeletons. It turns out the analysis of skeletons is exactly the same as short time theory, because for each atom in the skeleton, you're gaining a concrete power, positive power of L, and then your number of layers is pretty finite, and we should negatively recommend that L. So this is okay. So the main new ingredient there is that you are going to have a regular couple, which usually regular couple will correspond to a leading term. But here, if you have multiple layers, again there is something that there's some regular couple that does not correspond to leading term. So the leading term is 0. And these things I will call we're referring to them as a fake leading term in our paper. And let me explain those before we finish. So this term you can see how they occur. Okay, if for example, if you have time 0, okay, you have independence, K of the 4 cumulants are 0, A, K1, A, K2 bar, A, K3, A, K4 bar, 0, these are 0. And now what happens at time, tau? So if we think of this, if we think of the cumulant of 4, so this is not 0, because you're going to have, if you think of AK1 has a nonlinear evolution. So AK1 tau is a sum. Okay, so there is so sum, so L1 minus L2 plus L3 equals K1, and we have this integral from 0 to tau, e to the I of K1 square minus L1 square plus L2 square minus L3 square, T kinetic T. Okay, so we have this weights, and you have G L1, G L2 bar, G L3 T. So you have one of these terms here, and then you are going to have, because you are fixing this value K1, K2, K3, K4, how are you creating the correlations? If you match exactly L1 equals K2, L2 equals K3, L3 equals K4, then the contribution of this term, you're going to give a non-trivial contribution of these cumulants, which is natural because this cumulant is not supposed to be 0. We're having nonlinear interactions. So this means we're going to have this this term is basically, you're having this integral 0 to tau e to the I K1 square minus K2 square plus K3 square minus K4 square. And then of course, since this, K2 and this is linear, this GK2, this GK3, GK4, and you correlate those to get 1, and you get basically something, and of course the weights. Okay, so the okay, so there's one contribution that is this. Okay, so now let's say we start from time tau. If we start from time tau and we try to evolve the initial data at time tau, the initial ensemble at time tau, and we're looking at the 2-point correlations at time 2 tau. Okay, let's see. Now consider at time tau we're having this expected value of this A K1 of 2 tau square, expected value of A K1 2 tau times A K1 2 tau bar. Okay, let's say this guy is linear. The expected value of A sorry, this is a, so let's say this is a G, G, K1 of, let's say GK1. And then we have this AK1 2 tau, which is, let's say we have a cubic evolution of the data at time tau. We have this integral from 0 to, from tau to 2 tau e to the I, K1 square minus K2 square plus K3 square minus K4 square. This is T. This is T. And this is, I think this is negative. So let's say for this, this is GK, and this is a negative T square T. Okay, and then we have this, you know, K2 tau, AK3 tau, AK4 tau. This is this is T. Okay, now if you think of this is AK1, not GK1, AK1. And then ignore this. The random part of this contribution comes from the cumulant, you know, sorry, the correlation between K1, K2, K3, K4, and tau. Okay, and this correlation, of course, there are these binary correlation which you know come from the solution of the wave equation, but then there is a cumulant term which corresponds to this correlation, which is this. And if you plug in this, you're going to get, so plug in K term, you're going to get this. So integral tau to tau e to the minus I, let's call it omega, t, this is T1, dt1, and integral 0 to tau e to the plus I omega T2, dt2, and of course there is some omega, you know, some K2, K3, K4, and you have something, you know, some all these with omega. Okay, and this tells you what? So this is an integral. So integral, so T1 belongs to tau and 2 tau, T2 belongs to 0 and tau. Okay, and you have e to the I omega T1 minus T2, and of course your sum of this, you know, in K2, K3, K4. So if you remember these asymptotics, if you look at these exponential sums, again, this relies a bit on number theory. If you have these exponential sums, the leading term is going to have a delta function in this oscillation factor T. And so this guy, you're going to have a delta function of T1 minus T2. And now you see what? If T1 is integrated between tau and 2 tau, if T2 is integrated between 0 and tau, then this delta function is again 0. Okay? So this tells you that if you start from this correlation thing at time tau, you try to go to time 2 tau, then these cumulants will not contribute because of this time independence. On the other hand, if you start from this same cumulant at time tau, you try to go backwards to time 0, then this T2 will be 0 tau and T1 will also be 0 and tau, and this thing will not be 0 because they are in the same interval and they can be equal. Okay, so that's why this thing creates an error of time that this precise formula for this cumulant tells you, of course, there's negative tau here I'm omitting, but this cumulant tells you that you are getting the correct derivation when you go forward in time to 2 tau and not when you go backwards to 0. And this is also the source of these fake terms, graphically. This means that you have at time 2 tau, you have this 2-point correlation, but then you expand this time 2 tau. When you expand at time tau, you're having these 4-point correlations. Okay, and then when you go back from tau to 0, you're expanding this thing as this, and then you're matching this with this. So for example, you're matching this red with red, green with green, and this blue with blue. And you can ignore this because this is a linear evolution. It doesn't change anything. But then if you look at this picture, like if you draw in terms of couple, okay, this is a regular couple. By definition, this is a regular couple. But there is a time difference between this variable and this variable. Okay, so this is between tau and 2 tau. This is between 0 and tau. And because of this regular couple. It's a fake leading term. It's a regular couple, but its leading term, if you write down its asymptotics, is 0. And so this thing still vanishes in there because it's not appearing in the expansion of the wave equation. So this is the main new ingredient that we need in the long time case. Actually, here we just have 2 layers. In general, we're going to have any finite number of layers, and there can be arbitrarily complicated structure of regular couples. Non-regular couples we already know. There can be arbitrarily complicated structure of regular couples, and turns out that as long as the time intervals of one such branching node does not match, you are going to gain extra power, and this thing will go to 0 in the limit. And there is this extra analysis, extra number theory, and extra combinatorics involved in the study of these regular couples with different layers. And this occupies maybe like up to like 20-30 pages of the proof. And this tells you that these fake leading terms also not going to contribute. And then this allows you to control these gardens KG. Non-regular, you're good. Regular, but not matching the time layers is also good. And what you're left with the things that are regular and match the time layers, and those will turn out to be exactly the things that you see from the solution to the wave equation. Okay, that's all here.
Thank you very much, Hugh. Are there some questions? Sylvia, oui?
Can you repeat again, what is the sort of induction hypothesis that you can propagate in time?
Yeah, so
Bound on this K?
no, let me see. Not the bound, okay. It's okay, so we are doing truncations and we're having errors which are tiny, but if we ignore these issues, then really the propagates this fact that the correlations Q tau is a sum, the P and product A of this K, and the fact that the K is equal to the sum over all the gardens belong to a certain set, like a Q. This is a specifically, explicitly defined set of gardens of these explicit formulas Kg of the same variable. So you see, we need to propagate this exact formula and this exact formula by inducting on Q. Okay, of course, with up to error term, which will be tiny, but essentially this is this. It is not possible to proceed by just propagating the bounds on this K. We tried, it's not possible, but then really we need this explicit formula, and you see here, this explicit formula is a leading term, in the simplest 4-point cumulative, in the time tau, and this is a leading term. There are of course a lot more terms. So this precise formula of this term is very important to show that you can go forward to 2 tau and cannot go backward to tau. And so in general, you need to propagate this formula, of course, and this exact formula, right, with exact sets of G and exact Kg.
There are plus small terms.
The small terms are extremely tiny. You just ignore them. You can forget about them for any. These are not just like a polynomial. They are exponential. Plus small. Here, small means less than e to the minus L to the whatever, like log L to the 100 or something. It's tiny. It's less than any polynomial of L. So it's not the or whatever, or the size times the size of G or whatever. So it's not the bound. It's really like this really effective. They're really 0. So the only important thing is this expansion.
So one other time when you explained this, I thought I remember that you have a sort of way of selecting among the gardens those that you can throw out.
Well, this is a subset lambda Q. It's a there is a so that's why I'm saying what we call the canonical layer garden, which corresponds to the property in the Boltzmann case that any 2 particle lines kind of must be connected downwards. But there's a special set here, and this special set is constructed by a special process. Maybe if I was talking about in that time, I was talking about the construction process of this Latin cube, but it's an explicitly defined set.
Thank you.
Wait, yes, in the last step, when you consider large time, I have a question from what you have done. Can you understand the decomposition into chaos of your random wave? I mean, you start from a Gaussian,
Yes.
Gaussian, which does not remain Gaussian, but
Yes.
it is in some L2 space with a Gaussian measure, and you can make the decomposition into chaos. So the first chaos corresponds to the Gaussian field, and then you have a higher order. So can you understand what happened with respect? Or it evolves. It does not remain Gaussian, but it is in some L2 space with a Gaussian. So can you make the decomposition?
So in the short time, we have this explicit expansion.
But in the long time.
In the long time, what we know is these explicit formulas about the correlations. Right now I don't think we have an explicit formula of writing this solution as a combination of multilinear Gaussians. But so the information we have is all contained in these formulas. Everything here is an explicit object can compute, and using this you can express these correlations or arbitrary order up to a power of log L. This is kind of not very direct, but this is the.
Can you give estimates about this? If you think of higher and higher moments, can
Yes.
you give estimates?
For example, this K we have something like K to the L infinity less than, if you have K like with Q, the cumulative of Q modes is less than L to the minus beta Q for some positive beta. These kind of things is true. I mean, you cannot propagate it, but a posteriori you can prove this true.
Thank you.
I have a question about, I guess, the methodology somehow of the cutting algorithm. So you mentioned that you have a finite set of good structures.
Yes.
So I have several questions, but say the first one is it clear? How do you identify them? Do you know that you have an exhaustive list of all possible elementary good structures?
Yeah, basically we are looking at those structures with one atom or two atoms. Basically 2 atoms. I mean, occasionally we need 3 atoms, but these are very rare. But basically 2 atoms. Then we look at the possible degrees of 2 atoms. So for example, if you have a degree 3 with degree 3, that corresponding to a 5 vector counting problem. A minus B plus C equals constant. A C minus D plus E equals constant, and same for the quadratic equations. And this one you can have our bound number solution, by number theory. Okay, and you conclude that this is a good structure. And we are looking for others. So for example, if you have a degree 3 with a degree 4, this is not good. Actually, you'll see that this counting doesn't gain anything. But then if you have degree 3 with a double bond with degree 4, then this again will gain you something. So we just look at the simple thing with 2 atoms and consider possible degrees and do the counting problem and identify what is good and what is not.
Okay, so the first step is to look at all possible structures with 1, 2, or 3 atoms and classify them.
Yeah, we mostly look at 1 and 2, and the 3 is only because, like, for some cases, two atoms is not completely satisfactory. We may want to add more, but this is just we're not enumerating all the three atoms, only 2.
Okay, and then it's a bit philosophical maybe, but how do you make sure that in your cutting algorithm, I don't know, it will work out well? You see what I mean? So you cut out these nice structures at every step, but how do you make sure that there are sufficiently many of them that you can gain something, at least, for a large number of the possible cases? I have the feeling, I don't really see conceptually how you prove that you will consider all possible cases and that the good cases within your sum will be sufficiently many.
Okay, so there is so first of all, in the beginning, we believed it just by our belief. Like we believe that if you deviate from regular couples, then you should have enough good structures you can gain. This is just a belief in the beginning.
Mhm.
And later on, we realized that in the wave turbulence case, you can actually like by specifying the cutting algorithm, but in most cases, basically you can find a few kind of monotonic quantities. Like you can show that you can define certain quantities and you can show that how does these quantities behave in each cutting. So basically, you can show that these quantities kind of only decrease when you have these only decrease when we have these good things, and then in the other case you always increase, and then you go from something large to something zero, and it shows that you must have sufficiently many these good objects. So there are a few kind of monotonic kind of characteristic quantities that can calculate the increment. So by the way, so in the beginning of doing this Boltzmann thing, initially we tried to do something similar to find these quantities, but realized that it doesn't quite work, and there are many more kind of bad structure we need to exclude, and which eventually lead to a completely different, much more complicated algorithm for the Boltzmann. But for the wave kinetic, essentially it is this: like you just remove a good structure whenever you can, and then later on in the end, these characteristic quantities will tell you that you always have a good, enough many good structures.
Okay. Thank you.
Thank you again. Another question? No? Otherwise, let us thank very much you, Deng, again.